let's get started. Let me open up. I got chat right there. Okay. All right. So welcome back to lecture 2. Was everyone able to set up Echo? Is anyone still having issues with it? All right, awesome. If you would like to do it on CS1, I did get this running. If you do these exact commands, it'll work. I did it just like an hour ago. So I would suggest CS1 just because we're all gonna have the same experience, and I confirmed that the IT guy is he's working on getting Clang installed, which we will need next week. So that's good. Yesterday we just looked at code. I gave you all the project base. However, now we have to start modifying it. And even though I have posted my implementations on GitHub, and we'll look at those, the intention is not for you to just read the code and then turn in the code that I wrote, because then you didn't write it, compile it. So you should be writing code and taking notes on what changes we make, but ultimately this should be your own project. So just a heads up. I would like everyone to set up your Git repository on GitHub or GitLab or even your own personal hosted one. I don't care. As long as I can access it and I can see all your commits, we'll be good. Once you've done that, please email me the link it's charles@utdallas.edu. Again, it's not really going to matter until the midterm, but I might just dig through y'all's repositories just for fun. So anyways, so this is the current state of the compiler. On Monday, we looked at how we can scan in tokens and we can print them out just to see what they look like. So that's the pass example that I wrote, and this is the fail example. I didn't show it in the lecture, I should have, but if you pass in any unrecognized character like this period, you'll get a syntax error, which is what should happen. We don't want syntactically incorrect programs to get farther into our compiler. So it's pretty good. It's interesting, but it doesn't really do anything. We kind of just built a regex engine and a very special purpose one, and also it doesn't give you matches or anything. So kind of what we built right now is really not that useful. So the next step, we did scanning last lecture, and we called that lexical analysis. This is going to be syntactic analysis, and that's called parsing. That's the short name for it. And once we do parsing, this kind of opens up what we can do as a whole. We can start building more complex systems that have complex behavior. So let's do that. In this lecture, we're going to parse all our programs into an abstract syntax tree, and we'll talk about what that is. And then we're going to write a tiny little interpreter just to pass our tree into to see how we can use it. However, we are going to replace that interpreter next Monday when we start generating some LLVM. So let's start doing that. Let me pull up the notes on my screen. So in the last lecture, we said that we'd start off with our natural integer literals. We did that. And we have our arithmetic operators, plus, minus, multiply, divide. We've got that. And so yeah, that's what our scanner does. Let's take a look at the code to see what changed in this iteration. Again, okay, so let me just now I'm going to pull up the stream link so I can make sure there's no questions. Just see the questions as they happen. Okay. So this looks pretty different than what we had in the last lecture. Our first big change that you'll see is that we've moved our scanner object up to the global scope. The reason why we did this is because the global scanner, if you remember, held on to a token, like just a single token, and it would store that to parse in and etc. In multiple locations through the compiler, in various files that deal with parsing, we are going to be scanning in new tokens. So we need an object that we can share across files. This is where it started getting complicated. I mentioned that yesterday, that Python isn't that friendly at sharing data between modules, but we have to do it, so let's do it. The alternative is that you write a function that accepts the scanner, but then all of your functions accept the scanner, and it becomes ridiculous. So we also don't have that fancy with as syntax that we used. That's going to be a common theme. We're going to do something cool, and then later on we're going to take it out because we have to do something practical. I also just like writing Python flavor. It's fun, I think. And so the alternative is that this global scanner.open and global scanner.close, those are equivalent to having that with as syntax. And we can see that instead of calling global scanner.scanFile, we just scan in one token right here, and then we are going to call parse binary expression. That's a new function. So before we do this, we should get into a short review on language grammars and a bit about recursive parsing. So let's do that. So has anyone here not heard of a BNF grammar? Okay. So you will experience these in programming language paradigms and probably also automata theory, because those deal with scanning and parsing and whatnot a little bit. So when people design languages, one tool or format that they commonly use to describe what their programs can look like in that language, one of those tools is called the Bacchus Noir form, or BNF. There's also an extended version called eBNF, but it doesn't really matter in this case. And they describe valid blocks of code. So our goal, like we said in the last lecture, right now, and we're going to expand it later, is just to parse arithmetic expressions, like 1 + 1 or 5 times 3 + 2. Where an operator is accompanied by a number on both sides of it. There's no unary operators like plus in C-style languages. Not yet. We'll add them, but not yet. And again, it's not just that they're accompanied by numbers on either side, it's that they're accompanied by expressions. So a number is a valid expression, but so is an arithmetic expression. So this is what our BNF grammar is going to look like. We see that we've got this expression name right there, and when we put all this stuff after, what we mean is an expression can either be an integer literal, which we've got up at the top there, or it can be one of these 4 cases where we have an expression on either sides of an operator, and we use those quotation marks to denote like a literal string. We don't want anything else than just a star. We don't want, right now, we don't want anything else to represent multiplication or anything. So this is just a very, very simple BNF grammar for parsing arithmetic expressions. Can anyone point out one issue we might have with this grammar?
There's no stopping point. It's just constantly recursive.
That's not true.
Oh, yeah.
Integer literal is the termination.
Operator precedence?
Exactly. There's no operator precedence. So for our example, 5 times 3 plus 2, that's going to just go straight from left to right. So it's going to, or I mean, okay, in that case it doesn't matter, but if we had 5 plus 3 times 2, it would do 5 plus 3 first, assuming we did a left to right interpreter. And then it would add multiply by 2, which is not what we want. We want to do multiplication and division first, and then we want to do addition and subtraction, because that's how we do math on paper. So I'm going to go over parsing without precedence first, just because I want to get you introduced to it, and then we're going to talk about parsing with precedence. So in that example that I just showed, expression, that name we gave for all those cases, it's called a rule, or it's also called a non-terminal symbol, because it isn't guaranteed to terminate. Because remember, it could be a terminal symbol like integer, or it could be another expression. And then integer literal is a terminal symbol. So, oh yeah. Don't worry about the rest of that. Yeah, we just talked about how it doesn't do precedence. There are compilers that do accept a BNF grammar as input and then spit out a parser for you. So in the last lecture, someone on the YouTube comments asked about Lex and Yak, and those are the two parts of a popular compiler that people used for I don't know, decades. They're both old now. They're both outdated. People use Flex and Bison, or they use Antler or something else. But again, don't use those. That's not allowed. We don't really care about the BNF grammar that much. I'm going to be showing it throughout the semester as ours gets more complicated. But again, this is not really a theory class, so I'd rather us just write the compiler. And we're going to get much more familiar with all that theory stuff anyways as we kind of put it into practice. One more thing that we need to cover before we can do parsing is abstract syntax trees. So when you have the expression 2 times 3 plus 5 or any other arithmetic expression, it's kind of a misnomer to call them abstract syntax trees, because ASTs are supposed to be a simplified representation of a block of code. So if you pass in, a big function that has other function calls and complex mathematics in it, in C or C++ or something, an AST is going to, or your compiler is going to simplify the program as it reads it in, and then put it into an abstract syntax tree. And they do this because a lot of times programmers either are writing code verbosely, which honestly is good in my opinion, because we should be writing code for each other and let the computers figure out the rest. Or the programmer doesn't know what they want. So they might be, multiplying by 2 when a bit shift left, 1 bit would be faster. And so that's the kind of thing that putting it, parsing into an abstract syntax tree might do. So our parser is going to analyze the tokens that we scan in as we do it, and it's going to construct this tree that represents our entire program. I'll talk about this later, but sometimes you want multiple trees, and sometimes you don't. We're not going to. We're just going to have one big tree, just because it makes our architecture similar or simpler. The tutorial that I based a big chunk of this class on, ACWJ, a compiler writing journey, they suggest that you read this Medium article, and I've posted the link if you do want to. Honestly, I don't think it's really necessary. If you're comfortable with trees and you're comfortable with the idea of tree descent, then all this parsing stuff should come relatively easy to you. So let's look at an AST parsing example. Now let's look at our parser to see how we're going to implement all this. Oh yeah, one thing is you should be careful when you're doing all this yourself, because Python is a bootstrap language, which means when you start up the interpreter, the entire language is not kind of built in yet. So the interpreter will go into its own sources and it'll kind of build itself up and add more features to itself. And so part of the Python language includes a bunch of abstract syntax tree stuff, their own implementation. So make sure that you don't rename or name your classes after anything, because you'll get really weird errors. So that's a little interesting something about Python. So this is an abstract syntax tree example. Again, in this case, for arithmetic expressions, it's also a concrete syntax tree because it literally has every single bit of information that the input program did. But we're going to see over time that our trees get smaller than our programs. So when we traverse this abstract syntax tree for this program, we're going to do a depth-first traversal because we're just naturally going to build our tree with precedence eventually. I kind of do this out of order, but in this case, by doing a depth-first traversal, you see we're going to go down this left branch. That's a multiplication symbol at x right there. And so it's going to grab its 2, it's going to jump back over to the next branch, it's going to grab the 3, and it's going to go back up 1 layer, and it's going to compute, that operation on its 2 operands, or it'll generate assembly that does that. And then it'll go back over to the left, and then it'll finally sum them all up. Again, haven't discussed precedence yet, but you can kind of see that we want our trees to look like this because it's going to lend itself nicely to compiling and interpreting the meaning of the tree. Again, stop me if I'm going too fast or if you have any questions or anything. So let's look at the abstract syntax tree class. So this is our AST node class. We don't have a tree. We have a node because this is a recursive data structure. So each node is going to contain its own subnodes, its own children, right? So in this case, it's a binary tree, and you can see that because it takes in a left and right child. I didn't properly type annotate these. I forget if it's because of the 3.6 switch I did, but anyways, so we've got a left child and a right child, and I made these two-way tree links just because sometimes it makes things easier. One little thing, notice that we're taking a deep copy of the token. Remember, so our AST nodes, each node in our tree is going to store a little token of data from the program. So that's what that first argument is. If you remember, we have a global scanner that has a global token in it, and we don't want to have a reference to an object that changes over the lifetime of the compiler. We want to have a static version of it. So we need to perform this deep copy. If you don't, it's going to be frustrating. Ask me how I know. And the rest of this is pretty just standard for any binary tree stuff that you've seen before. And then finally, we have these two functions that just create special forms of an AST node. So this one creates just a leaf, which is at the bottom of the tree, no children. And then this one creates a unary AST node, which means it just has one child. there's really no reason to have these. It's more because, again, I built this compiler looking at a few other compilers, and they all kind of, I mean, they were written in C, so they kind of needed to do all this setup in a function, or else things would get complicated, so I did it too. But so that's our AST node. Again, I did this a little out of order, but I think it'll be okay. Let's look at how our parser should work for, in this case, the program 3 plus 5 plus 6. So our compiler is going to start up. It's going to do all the setup that we saw in the main function. And then it's going to start parsing. In our grammar, the first thing we should always reach is a terminal node. We're not doing any postfix or prefix stuff yet, so we should always reach a terminal node first. If not, we're going to throw some kind of error, I guess a syntax error, right? A syntax error, a parsing error. And in 3 plus 5, that little first chunk of the program, 3 is a terminal symbol. So we're going to parse that terminal symbol into a token. It's going to be an integer literal token, and it's going to have the value 3. And we're going to shove that into an AST node, and we're going to call it left, just arbitrarily. Not arbitrarily, kind of arbitrarily. I don't know, depends on what you see an AST as in your mind. And then if we see that we've reached the end of the file, so if our program, for example, only contained the number 3, that's a valid expression, so we would just return left as our expression. Otherwise, we want to scan the next token, right? And the next token should be an operator. Remember, white space doesn't matter in our language yet, so the next character that we read in should be a plus, a minus, a multiplication, or a division. And then we're going to recursively scan the next expression. We don't know how long our expressions are going to be. We could, say, oh, your expression has to be this many symbols maximum, but that wouldn't be a very useful language. So we're going to recursively scan the next expression, and then we're going to store whatever comes out of that recursion into a variable called write. And then finally, we are going to create an AST node with left and right as its children, and we're going to store the operator that we parsed into that AST node's data. And we're going to look at this in a second. Yeah, and we just went through this, but let's take a look. I want to do this right here. So what we had 3 plus 5 plus 6, right? Okay, so I'm just going to step through what the compiler should do. So first thing is that we see this token 3, right? And you remember we said that we haven't reached the end of the file, so we should scan another token in, and we should get an operator. And we do. We find this plus operator right here. And we kind of just store this over here. We don't want it yet. But 3 becomes this left object over here. We're going to recursively scan again. And so we've taken in the 3 and the plus already, and so we've got a 5 plus 6 left. We see a 5, which is good because we shouldn't see an operator, because remember, always need to see a terminal token first. This is going to become our left for that little recursion chunk right there. We're going to do the same thing. We find a plus, store it over here because we don't need it yet. Do the same thing, and we find a 6. Boom, we found our end of file, right? Found our end of file, and that's an expression on its own. 6 is an expression. So we can return that from that level of recursion, and we're going to call that the write value. We're going to create an AST node with plus as its value, and then we're going to give it the children of left and right. And we've reached the end of the file again because there's nothing left to scan in. So this is our right value for this level of recursion. Create a AST node with plus as its data and give left and right its children. And ta-da, we have an AST node that we've successfully parsed into our expression that we've successfully parsed into an AST. And remember, there's no precedence here, so if this was 3 plus 5 times 6, or let's do, just for this example, let's do 3 times 5 plus 6. We end up with an AST that does not recognize precedence because if we're doing recursive descent, we're going to parse the lower, or we're going to compute the lower values first. So it's going to add 5 plus 6, and then it's going to multiply 11 times 3, which is not what we want. And again, I mean, if you did it so that you switched the left and right, this is why I said it doesn't really matter. If you switch left and right, then this expression would compute properly, but then 3 plus 5 times 6 would not compute properly. So again, just keep in mind that what we're doing right now does not support precedence, but we will add it in a bit. So we can see that the routine we thought up in our head handles well. I suggest, if you really, if you want to get a hang of it, maybe try it on a couple other expressions. See how it doesn't work for precedence. This is my implementation. We're going to look at that, and then we're also going to look at the a compiler writer's journey implementation real quick. Oh. So this is it. Remember, we parse a terminal node. Again, that's kind of an implementation detail. I might show you that in a second, but parse a terminal node because we always expect that first. Store it into a value called left. If we reach the end of file, we have a special token type for that. Then we're just going to return left as our value. Otherwise, we're going to just store the current type of our the type of our current token, which should be an operator, because parse terminal node is going to scan in the next token for us. We have to do just another manual scan just because of how I wrote the terminal node scanning. And then we're going to parse a binary expression, which is the function that we're already in right now. Store it into right, and then return an AST node with our operator type, our left child, which we parse at the top, and our right child, which we recursively parsed right here. And I'll show you the C version, just because. So this is, don't worry about that. This is what we need right here. So you can kind of see the structure of it is very, very, very similar. Just some function names are different. Read in, he calls them primary tokens for some reason. And that should be an integer literal. Call it left. If we reach the end of file, return left. Otherwise, store the current type of our operator. Scan another token, recursively scan the right side, construct an AST node, and then return it. So that's just some, example of the similarities. So we've written a naive parser, and soon we're going to write a tiny little interpreter for our ASTs. But we want to do precedence because without precedence, it's kind of horrible. Don't implement what we just did because that didn't have precedence. Or honestly, No, you have to do precedence. Sorry, I was gonna say maybe not, but no, it is. The thing we're gonna go over in just a second is really cool. So I'd like all of you to do it. So, does anyone have any ideas on how we could implement precedence? Hinted as something to do with the grammar that we defined earlier. Nope. So, let's see if I have on the next slide. We want our BNF grammar to reflect precedence. And this is the way we would do it. We would separate our expressions into different tiers. And so this multiplication expression, that's going to handle our multiplication and division. And it's the only rule that has, I guess you could say, access to integer literals. So if we passed in 3 plus 5, it would first go through expression, which matches to an add expression. There is a plus there in that add expression, and so we parse in 2 more add expressions on either side. But those would both go to multiplication expressions, which are integer literals, because those are the only things that can be. And then if you did 3 times 5 plus 6, you'd immediately go from add expression straight to multiple expression, and then you'd do your multiplication first, and then you'd go a step back up, and then you'd do addition. So this is how your compilers are going to generate your parser for you. They're going to give you a chunk of code that really just emulates, the meaning behind a BNF grammar, and that's a perfectly fine way of doing it. There are other ways of doing it that aren't based on recursion, and we're going to be doing one of those. Firstly, because it's much easier to manage. Can you imagine, let me show you the BNF grammar for C. It's enormous. Can you imagine having functions for every single one of these rules? For a computer to generate the code to do that for you is fine, but we're not doing that. We're writing it from scratch. So we have to be smarter about this, because if you spend all your time dealing with recursive descent parsers by hand, you're going to be doing a lot of bug management, and it's just going to be a whole pain in the neck. Thankfully, there's another way to do this that is not entirely based on recursion. And it's arguably simpler, I guess, depending on who you ask. And it's called Pratt parsing. And that lets you parse with precedence. So let's talk about it. I'm going to say it's kind of complicated. I say it's simpler because it's a lot less code to write. But the logic behind it is not as intuitive as recursive descent parsing. Did everyone kind of understand the idea behind the recursive descent parsing and how it adds precedence for us? Right, because it just kind of intuitively makes sense. Pratt parsing is really good at dealing with expressions and precedence, and that's why we're going to do it. And recursive parsing is also good, but it's really better at dealing with structured statements, which is why you saw so many rules for C. So, your for loops and all that. Most C compilers are probably going to do it with recursive descent parsing. And so a good compiler is going to mix Pratt parsing and recursive descent parsing where it makes sense. And the general idea behind Pratt parsing is that we store a table of precedence values for each of our operators, instead of having an explicit function for each of those. I've linked an article in the slides if you'd like to see the kind of mathematical intuition behind Pratt parsing, but my hope is that when I show you the code, it's kind of going to make sense, or at least if you can't inductively build on the reasoning behind why it works, you'll at least be able to deductively see why it works. Again, we're not going to go too much in depth, but we're going to do enough to cover our implementation in Echo. So, let's check out our main function again. I think I have to go to precedence, that's right. So this is another branch. I did two just because I wanted to show you the difference between precedence parsing and non-precedence parsing. So we didn't look at the past one too much, but the main difference here is that we passed in a 0 to this parse binary expression function that we looked at in a second. So let's take a look at parse binary expression and see why it worked. Let's see. Darn. Echo parsing expression. So we've still got our scan in left as a terminal node. That's fine. Still store in our current operator type, and then we are going to check if there's an end of file. So that's all the same. But we've got this while loop here, and we didn't have one before. So crowd parsing is kind of going to mix recursion and iteration in a way that kind of might seem counterintuitive, or that you might end up at a point in the while loop where you're at the end of the file and you shouldn't be. But you're guaranteed not to do that. You're always going to have a value where you should, which is nice, as long as your program is syntactically correct. So let's take a look at the precedence values right here. So I've just made a dictionary that maps our operators, our token types for the operators, and we match them to a number. I picked 12 and 13 because I promise later on in the course you're going to be looking this up a bunch. C operator precedence table. Choose 12 and 13 because those are the values. No, I did it in purple. I guess. Let's see. Let's look into. Okay. Wait, is that the same? Okay, yeah. The difference between this table and this table, you can see, is that the direction of the numbers is flipped. I did that because it makes that while loop a little simpler, but you can still use this table to look at. You don't have to dig through my other compiler's documentation. But addition and subtraction have a value of 13 for their precedence, and multiplication and division are going to have 14. And we just say that.
So why do you assign them 12 and 13?
Because there's all these other operators and other parts of the language that.
No, I mean instead of 13 and 14.
Oh, because this is one indexed and it's 0 indexed in the other one. So, sorry, yeah, a little confusing, but just indexing. But yeah, so there's all these other operators, and we want them to do. We don't want them to collide with each other when we have big complex expressions. So we're just going to put them in this big table. And again, we're going to add, basically all of these things to the language. So you're going to be messing around with your operator precedence table a bit. But so yeah, this is another table. Nothing crazy. If you you can just pass in a token type into it, and it'll give you a precedence value. I wrote a little error checking function around it just to check if the node type, the token type you gave it, is not a valid operator. Then it's going to raise a syntax error because you did something wrong. Yeah, so it's just going to check the precedence value, and if it's bigger than the precedence of the previous token, which we have passed into us up here, And remember, we start out with a 0, so everything should be bigger than it. As long as that happens, you're going to scan in a token. Remember, we did that in the recursive version of this right after we checked for the end of file. Again, we're going to parse a binary expression, and we're going to pass in the operator precedence of our current node type, and that gives us the right half of our abstract syntax tree. And then you just, the difference here is that instead of returning the parent of that left and right with the operator, is you assign that to the left variable again, and then you're just going to do this while loop over and over and over until you hit the end of the file. So you can kind of see how it's kind of modeling the recursion that we had before. The nice thing about this is that it's a tiny bit more efficient, and it's much easier to maintain than having a bunch of recursive function calls. So, and then again, check the current token type. If we reach the end of the file, break, and then the only thing we have after that is to return left. Just talked about all that. Okay, so we're almost there. We've built an abstract syntax tree. Let's check back in main and see what we do with it. Hint, we're going to be writing a tiny little interpreter, which should be super simple. So we define it right here, and then all we're going to do is we call that function on the AST that we got out of parse binary expression. So let's look at this function. We can see that, is everyone familiar with the structure of a depth first traversal? You just know that it's going to go down all of the left branches first, and then it's going to jump to the next closest right branch, and it's going to back up, and da-da-da. And this is literally exactly what it is. The first thing we do is if we can move left, we're going to move left. If we can move right, we're going to move right. And after we check both of those, we know that we've got some abstract syntax tree node that we're looking at. We check for any of the 4 operators we've got, and we're going to add our left and right values together, or subtract, or whatever. Remember, we're doing integer division, so you need that double slash in Python if you're going to do integer division. And then if it's just an integer literal, then you can just return that value. Otherwise, if you accidentally put an end of file token into your AST, you're going to get an error. And that's it. That's really as simple as it gets. Tiny little recursive descent algorithm over our AST, and it is going to, guaranteed, give you the value of an expression with precedence. So, I can show that real quick. Scripts, or let's see. So 2 plus 3 times 5 minus 8 over 3. Let's run that through Python.
Why option is C?
It means do inline. So you give it,
I see.
you just give it a something you would pass to the interpreter, and it'll do it for you. So this evaluates to 15, and let's do scripts run examples parse test 1. 15. That's the code I just showed you. No changes. And we got it. I can show you another example. See, this one's got a bunch of funky white space. It's got a leading 0 on that 8 in the bottom left. We are going to deal with that later. In most modern languages, a leading 0 means you want to do an octal integer constant. like hexadecimal or binary, but base 8. We're not handling that yet, but we will in the future. Our compiler says 29. Python says 13 minus 6 plus 4 times 5 plus 8 over 3, 29. Ta-da. And I think 3, 4, and 5 should throw errors. Yeah, so this one, see, we've got these 4 operators in a row in the middle right there. Let's run our interpreter on them. Syntax error. Okay, I mean, the first error is over here. We were expecting an integer. Oh, first error is right here. We were expecting an operator in between those two numbers, but after our first integer literal, we expected an operator, but we got an integer literal. And parse test 4 and 5 throw other various errors. But so I mean, there you go. We've written the foundation for our compiler, and I know it doesn't seem like it right now, but with that prat parsing, we've kind of opened the way to implementing variable assignments, for loops, while loops, and a little bit of stuff we need for function calls. So that's just keep that in mind. Let me go back to the slides here. Yeah, and so you might be asking yourself, why didn't we just write a tiny little calculator that hard codes? Look for an integer, then look for a operator, then look for another integer. We could have, and it would have worked. It would have been a lot easier. But again, we've laid the groundwork to do a lot more complex things, which is what we want. By the beginning of February, that's what, week after next? Anyone know? I don't know. Next week?
Wednesday next week is the 1st of Feb.
Okay, so I'm going to say the week after next, we are going to have a fairly substantial chunk of the C programming language able to be compiled, assuming you follow the pace of the lectures. And it would be nice if you did, but it's fine if you're a lecture behind or anything. I mean, we've got all semester to do this. I think by 2 weeks from now, we should have if statements going, we should have while loops going. We might even have a very rudimentary function declaration going, if that's correct. So there you go. That is the end of week 1. The optional homework for this week is to implement bit shift operators left and right. Should not be very hard. In fact, I've given you a very comprehensive hint right here. You just need to create operator tokens. You need to give them string values so that our scanner can recognize them. You need to add their precedence values to the precedence table, and then you need to add a chunk to the tiny interpreter we wrote. And that's an example of how cool prat parsing is. To do this with recursive parsing, you need to add more functions. And in this case, it's much, much simpler. So, just a little personal note. If you found this week to be a lot of work, don't worry. Only real due date is the end of the semester. And the other thing is that these first 2.5 weeks are going to be the most jam-packed, because I want to get to the cool stuff. I don't want to bore you with scanning and parsing, because if you wanted to do that, you would probably just take the compiler course that's officially offered at UTD, because that's what they do. They go over a lot of scanning and parsing, which is fine if you're into that. I'm not. I think the cool part of a compiler design class should be code generation, because mapping high-level structures and classes and blah, 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 all down to assembly, these fundamental operations that our CPUs do, I think that's super interesting. And so first thing on Monday that we're going to be doing is starting to generate some LLVM. That one is going to be a jam-packed lecture. So please attend it. Please ask many questions, because there's a lot of material to cover in that one. And again, you've got a long time to finish the stuff that we just talked about in today's lecture. Try to keep up with the lecture pace. Again, if you're behind, it's not a big deal. And then after a couple weeks from now, most of what I cover is going to be those like optional 50% of the topics left that you can choose half of to do to complete the course. And you know, if you want to have a C compiler that accepts most C programs, I suggest that you do all of it. But if you're lazy or busy, both of which I completely understand, then you don't have to do all of it. Please come see me during office hours if you have any questions. And start thinking about what kinds of special features you'd like to add if you're going to design your own language. Or what keywords you're going to change, because that's a fun little thing to do, honestly. I'd love to hear all your ideas. I'll tell you how feasible they are to my knowledge. And if you have any questions, again, email me. I should email back pretty quick. So that's it. Are there any questions? So the goal before the next lecture for anyone who wants to stay with the pace is, I'll show you how I would do it. You're going to want to update your copy of the compiler so that it does the same thing that this branch 3 is going to do. And the way I would do that is I would compare this new branch to the last copy of the branch you have, which is the project base. It should be in here. This highlights every single line that changed between those two versions. So again, don't copy, because if you just copy my code, that's not the point, and I'm not going to give you the certification. But look at it, see what changed, and do it yourself. I would love to hear any improvements you've made on it, because I like hearing that stuff. So that's what you should be aiming for.
So we can't copy your code, but we can have something similar, but it has to also be different.
Yeah, have some.
It also has to be in a different language.
No, it can be in the same language. You can keep building on the project base. That's why it's there. But just don't copy word for word. I'll know if you just change the variable names, because I've been working on compilers that have the same exact structure of this for, I don't know, a year and a half now. So I'll know if you just copied exactly what I did. And you can copy the structure, copy off the lecture that I just gave, because that's what the lecture's for. Just don't do it word for word. And I would like to see personal touches made to it. So.
Can we start by copying word for word in another language?
I would prefer, no.
As a base.
As a base to build off of? So you mean you want to...
Basic parsing.
What do you mean?
No, I mean, we're going to have to use the same logic.
Correct. Use the same logic. Use the same structure that we just talked about. Don't do it. Don't copy. Don't do it word for word. I'm posting all this here because, I glossed over plenty of implementation details during the lecture. So those are important to actually write the code, but I'm not going over those, in the lecture. So that's what this is for.
This is just out of curiosity, but what IDE did you use?
What IDE?
Or did you just code in the terminal?
For Python, I'll do it in VS Code. This isn't Python, but I think the only thing I would write in Vim regularly would be HTML, just because sometimes I do HTML stuff, but this is for another class I have. Yeah, VS Code is fine. It integrates well with linters and stuff like that. So.
If we're running the parsing part of the echo in a different language, do we have to like rewrite everything in the language that we're running it on, or do we have to find a way to connect our parsing file that's written in a different language to like echo somehow?
No. You don't have to use echo. If you want to do it in a different language, you're not going to be able to use echo. If you want to do it in Python, I suggest you just use echo because I've set up a bunch of the hard stuff for you. But
What kind? Bunch of the hard stuff like what? Like, I remember you going over the daily details of it.
error generation or error printing and stuff like that. That's what echo provides. Rudimentary things that aren't unique to compiler design, that are just annoying parts, or maybe fun if you like writing boilerplate, but those parts of software development that I didn't think you should have to worry about. Argument parsing, error handling, stuff like that. I've got a question on the YouTube. How do I SSH into CS1 if I don't have a UTD login? I'm sorry, that's not possible. It's just for UTD students. However, there are 1,000,001 ways to use remote Linux servers because plenty of online places offer them. Or just use a virtual machine if you know how to set that up. Okay, any other questions? Did you have one? Sorry, I thought I saw a hand. No, okay. So we've got about 20 minutes. I'm gonna end the stream, and then I'll walk around and I'll help if any of you want to start working on the code right now, then I'll help guide you. If not, that's fine.